In the vast silence of the universe, there is one force that has never spoken aloud, yet has written every line of the cosmic script. It is gravity, the invisible sculptor of all that exists. It gathers dust into stars, stars into galaxies, galaxies into clusters. It bends the path of light, commands the rhythm of planets, and locks time itself to the curving fabric of space. But within its quiet dominion lies a paradox, for gravity is not only the hand that binds, it may also be the breath that scats. Imagine, for a moment, the universe turning against its own foundations, where the great attractor that holds the Milky Way together begins to push it apart, where galaxies drift not toward one another, but away, as if repelled by some hidden tide, where time itself seems to stretch faster, its moments fleeing into an unreachable horizon. This is no fantasy, no invention of the imagination. It is a possibility whispered by equations, measured by telescopes, and recorded in the faint afterglow of the Big Bang. The cosmos, once thought to be eternal in its balance, is revealed to be fragile, unstable, and perhaps destined for a fate stranger than its birth. What happens when gravity turns inside out, when the force that binds all things begins to unbind them? The answer is written not in myth, but in physics, in the cold, precise language of science, and in the haunting questions that still remain. Gravity first entered human thought, not as an equation, but as a sensation. The weight of stone in the hand, the fall of an apple from a tree, the pull of earth on every step taken across its soil. For centuries it was assumed to be ordinary, a constant presence so familiar it barely seemed worthy of deeper inquiry. Yet hidden beneath this everyday force was the quiet truth that it governed the fate of worlds. It was Isaac Newton who first unveiled its reach. In the 17th century, in the wake of the scientific revolution, he imagined a universe in which the same force that dragged an apple to the ground also pulled the moon in its endless fall around Earth. Gravity, he declared, was universal, stretching without limit, invisible yet absolute. It was an elegant law, one that painted the cosmos as a grand machine of precise orbits and predictable motion. For more than 2 centuries, Newton's vision stood unchallenged, a framework that explained the rise and fall of tides, the paths of comets, even the delicate clockwork of planets circling the sun. And yet, beneath its success, questions lingered. Newton could describe what gravity did, but not why it existed. What was this mysterious action at a distance? How could a force leap across emptiness, pulling on bodies without any medium to carry its influence? For generations, these questions remained unanswered. Hidden in the margins of physics, it was Albert Einstein who dared to rewrite the script. In 1915, with the publication of his general theory of relativity, gravity was transformed. No longer a force that reached across space, it became the very shape of space itself. Massive objects, Einstein showed, curved the fabric of spacetime, and other bodies move along these curves. The Earth does not orbit the Sun because it is pulled, but because it rolls through a valley in space-time carved by the Sun's presence. Light itself, once thought untouchable by gravity, was shown to bend along these warps. The universe was no longer a machine of gears and pulleys. It was a vast, dynamic fabric, alive with invisible architecture. Einstein's theory predicted a cosmos that should not be static. Space, being flexible, could stretch or contract, carrying galaxies with it. Yet Einstein, guided by the prevailing belief that the universe was eternal and unchanging, hesitated. He introduced into his equations a delicate balancing term, a cosmological constant, to hold the universe in place, to counter gravity's attraction and preserve a timeless cosmos. It was a mathematical invention, a silent patch on the grand equations of relativity. And for years it seemed a reasonable assumption, but the universe was already whispering another story. In the 1920s, atop Mount Wilson in California, Edwin Hubble turned his telescope toward the faint smudges of light beyond the Milky Way. He found them to be galaxies, entire island universes, and with careful measurement of their spectra, he discovered something shocking. They were moving away. The farther the galaxy, the faster its retreat. The universe was not fixed, but expanding. Einstein's constant was not a necessity. It was, as Einstein himself admitted later, his greatest blunder. From that moment, the cosmos was revealed as a place in motion, its fabric stretching in all directions, carrying galaxies outward in an ever-widening sea. The great debate shifted. If the universe was expanding now, had it been smaller once? Had it begun from a moment of unimaginable density and fire? Thus the idea of a Big Bang was born, and gravity took its place, not only as the sculptor of stars and planets, but as the central actor in the drama of cosmic history. For decades, astronomers assumed the expansion would slow. Gravity, though weakened across vast distances, would still act as a brake. The combined pull of galaxies, dark matter, and every particle in existence should eventually counter the outward rush, perhaps even reversing it in a cosmic collapse. The universe was a struggle between expansion and attraction, and physicists believed they knew which force would eventually win, but hidden in the faint light of dying stars. A different message awaited in the late 20th century. Astronomers turned to type Ia supernova, stellar explosions so bright they could outshine entire galaxies. These supernovae burn with remarkable uniformity, serving as cosmic beacons, their brightness revealing distance, their spectra revealing velocity. By comparing how bright they appear with how fast their host galaxies are moving, astronomers can measure the expansion of the universe across cosmic time. What they found was not the slowing they expected. The light of distant supernova carried a different story. The universe was not only expanding, but accelerating. The farther back in time they looked, the slower the expansion appeared. Somehow, in the recent few billion years, the cosmic engine had changed. Gravity, the eternal binder, seemed to be losing its grip, or perhaps turning against itself. The discovery shook the foundations of physics. In the data of faint, dying stars lay the first hints of a reality stranger than Newton could have imagined, stranger even than Einstein dared to predict. A universe where the invisible hand that once held galaxies together now seemed to be pushing them apart. A universe where gravity, in some unfathomable sense, had turned inside out. The late 20th century had carried physics into a place of unprecedented confidence. The great pillars of science, quantum mechanics, relativity, thermodynamics, stood like towering monuments, explaining phenomena from the structure of atoms to the orbit of galaxies. Though gaps remained, the sense was clear. The cosmos was legible, its hidden logic increasingly within reach. And then came the discovery that shattered that certainty when the light of distant type, Ia supernova, was carefully examined in the 1990s. The results at first seemed almost unbelievable. Teams of astronomers, working independently across the world, found that these explosions appeared dimmer than expected, not because their light had faded, but because they were farther away than models had predicted. The galaxies that housed them were not merely receding, they were receding faster than they should have been. The universe was not slowing in its expansion. It was racing outward with an acceleration that defied all expectations. This was no subtle discrepancy. It was a revelation that overturned a century of assumption. For generations, cosmologists believed gravity to be the universe's dominant voice, a force that could only attract, never repel. On the grandest scales, matter was thought to be the brake on expansion, a tether binding the cosmos together. Yet the data spoke otherwise. The universe was not bound, but unbound. Something was acting in opposition to gravity's familiar pull. Something that pushed galaxies away from one another across the void. It was, in essence, gravity behaving as if it had reversed polarity. For Newton, this would have been unthinkable. His equations captured gravity as an ever-present attraction, the universal glue. For Einstein, too, the revelation would have been unsettling. Relativity allowed space to curve and stretch, but the expectation remained that mass would slow this. Expansion, not accelerate it. The acceleration implied a form of pressure in the vacuum itself. A pressure not of matter, but of emptiness. The magnitude of the shock can scarcely be overstated. In an instant, nearly every cosmological prediction was called into question. If the universe was accelerating, then its fate was not to collapse into a fiery end, but to expand endlessly. The cosmic scales had tipped, not toward closure, but toward dissolution. Stars and galaxies, once thought destined to fall back together in a final convergence, would instead drift forever apart, their light fading into a cold and endless night. For physicists, the conceptual wound cut even deeper. What force, what field, what property of reality could drive such behavior? If gravity was supposed to draw, what invisible agent was pushing? The first answer, tentative yet profound, was named dark energy. It was not matter, for no substance could behave this way. It was not radiation, for radiation thins as space expands. Instead, it seemed to be something woven into the very geometry of space-time, an energy that did not dilute with distance, that did not fade as the universe grew, but remained constant, fueling acceleration as if the void itself were alive, with pressure. And yet, even as this concept took shape, it remained almost unbearable to accept. Physicists are trained to seek symmetry, order, mechanisms hidden but ultimately explainable. Dark energy was none of these. It was a placeholder, a name given to ignorance, a sign that the heart of physics had been caught unprepared. The shock was philosophical as much as scientific. Gravity had been trusted for centuries as the faithful sculptor of structure, the guardian of permanence. To see it apparently inverted, attractive in the realm of planets and stars, but repulsive across the cosmic horizon, was to glimpse a duality that unsettled the mind. How could the same force play two opposite roles? Was the universe itself unstable, or was human understanding merely incomplete? For many, the echo of Einstein's abandoned cosmological constant returned with a haunting resonance. Once dismissed as a mistake, it suddenly seemed prophetic. His mathematical patch, designed to freeze the universe in place, looked remarkably like the mysterious agent now accelerating the cosmos. What Einstein had cast aside as error might have been the first glimpse of truth, but the true wound came, not from history, but from the scale of the unknown. Calculations of quantum field theory suggested that the vacuum should indeed possess energy, yet the predicted amount was wrong, not by a factor of 2 or 10 or even 1,000. It was wrong by 120 orders of magnitude. the most colossal mismatch between theory and observation in the history of science. This was not a mystery that could be brushed aside. It was an abyss, yawning at the center of physics, reminding scientists that the universe was stranger than their boldest frameworks allowed. For the public, the revelation was often framed as wonder, the discovery that the cosmos was expanding faster and faster. But for those who understood its weight, the feeling was closer to vertigo. To live in such a universe was to exist on the edge of comprehension, in a cosmos driven by forces that defied the known rules. It is difficult to imagine a greater reversal of expectation. The force that had guided stars, that had bound galaxies, that had shaped the very arc of the cosmos, was no longer simply the pull of matter. It seemed to harbor within it an opposite destiny, one that pushed, scattered, and unraveled. Gravity, once thought the most stable of companions, revealed itself to be paradoxical, capable of inversion, capable of betraying the very intuition upon which all physics had been built. In that moment of shock, cosmology was reborn. The universe was no longer the predictable machine Newton envisioned, nor the elegant fabric Einstein described. It was something wilder, more unstable, charged with hidden currents, something whose foundations might themselves be shifting beneath the equations. The name dark energy carried the tone of humility, an admission of ignorance. But beneath the term lay the deeper truth. Humanity had discovered that the cosmos itself was stranger than its guardians dared believe, a universe where gravity, the most ancient of forces, might contain within it the seed of reversal, the possibility that one day all that is bound will be unbound. The first glimpse of cosmic acceleration had left scientists reeling. Yet science, by its nature, does not stop at revelation. It demands confirmation, detail, measurement, and the long, patient work of turning shock into understanding. If the universe was truly expanding faster and faster, then its fingerprints would be written everywhere, in the light of galaxies, in the patterns of cosmic structure, in the very afterglow of creation itself. And so a new phase began, a deeper investigation into the strange force that seemed to invert gravity on the larger scales. The maps of the heavens, the late 1990s and early 2000s, witnessed a surge of astronomical ambition. Telescopes on Earth and satellites in orbit became detectives, each tracing a different clue to the mystery. Among the most influential was the Sloan Digital Sky Survey, a vast program that set out to map the cosmos in unprecedented detail. Night after night, its telescope in New Mexico scanned the sky, recording the positions and spectra of millions of galaxies. What emerged was not a random scattering of light, but a tapestry of structure, cosmic filaments stretching across billions of light years, clusters of galaxies bound like knots along a hidden web. This great architecture, the cosmic web, carried within it a record of expansion. The spacing of galaxies, the clustering of matter, the subtle ripples in distribution, all spoke of a universe not static but restless, its fabric stretched by an unseen hand, echoes of the beginning. Yet the most decisive evidence came not from galaxies, but from light far older. In the 1960s, Arno Penzias and Robert Wilson had stumbled upon a faint microwave hiss, the afterglow of the Big Bang itself. This cosmic microwave background, the CMB, was a frozen remnant of the universe's infancy, a portrait of the cosmos when it was only 380,000 years old. Decades later, satellites such as WMAP and Planck transformed that discovery into something profound. By mapping the CMB across the entire sky with exquisite precision, they revealed tiny fluctuations in temperature, ripples less than 1 part in 100,000. These were the seeds of galaxies, the imprints of quantum fluctuations stretched across the young universe. But encoded in those ripples was more than history. The geometry of space itself, the balance of matter and energy, the rate of cosmic expansion, all could be read from this ancient light. And the story it told matched the supernova. Roughly 70% of the universe was not matter, not dark matter, not radiation, but something else entirely. Something that acted like a constant energy filling space, driving acceleration, something that bore the signature of gravity turned inside out. Supernova confirmed, meanwhile. Teams of astronomers refined their surveys of supernova. Each new explosion added data, reducing uncertainties, sharpening the curve of expansion through time. The dimness of the most distant type, IA supernova, was no fluke. It was consistent, relentless, undeniable. The acceleration of the universe was real. The picture grew sharper, yet stranger. Expansion was not a simple curve, but a history of shifting balance. For billions of years after the Big Bang, matter dominated and expansion slowed. But as galaxies grew more distant, the density of matter thinned, while the mysterious energy of the vacuum remained constant. Slowly, invisibly, the balance tipped. A few billion years ago, the universe crossed a threshold. Matter yielded to dark energy, and acceleration began. It was as if the cosmos had 2 chapters, one of gathering and binding, one of scattering, and release the balance of the cosmos. The numbers that emerged from these studies painted a startling portrait. Only about 5% of the universe was made of ordinary matter, the atoms of stars, planets, and life. About 25% was dark matter, unseen but gravitating, sculpting galaxies with its invisible mass. And the remaining 70%, the dominant share, was dark energy, the unknown agent of acceleration. The result was humbling. Everything humanity had ever touched, seen, or measured directly was but a sliver of reality. The majority of the cosmos was hidden, not only unseen, but behaving in ways beyond comprehension. Patterns in the web. The distribution of galaxies revealed further clues. As light from distant quasars passed through intergalactic gas, it left faint absorption marks, forming what astronomers called the Lyman Alpha forest. The spacing of these lines traced the scaffolding of the universe. And within that scaffolding, scientists detected a subtle but crucial pattern: baryon acoustic oscillations, the frozen echoes of sound waves from the early universe. These oscillations acted as a standard ruler, a cosmic yardstick imprinted in the clustering of galaxies. By measuring their scale across different epochs, astronomers could track how expansion unfolded through billions of years. And again, the verdict was clear. The expansion was not slowing, but accelerating, driven by a force that seemed to act against gravity's pull. A universe of layers, every method, supernova, the cosmic microwave background, galaxy clustering, converged on the same haunting truth. The cosmos was dominated by an unknown energy, a pressure intrinsic to the vacuum itself. The deeper the investigations went, the more consistent the anomaly became. There was no escape, no alternative explanation that fit the data as well, and so, slowly, reluctantly, the scientific community embraced the reality. The universe was not governed solely by attraction. On the largest scales, it was ruled by repulsion, a repulsion born not of matter, but of the void itself, a quiet realization the investigation deepened, but the mystery remained. Dark energy was not observed directly. It was inferred, like the presence of wind seen in the sway of trees. It was not measured in laboratories, but revealed in the vastness of cosmic structure. Its fingerprints were everywhere, and yet its nature was nowhere to be found. To many, this duality was unnerving. Physics had grown accustomed to triumphs, the discovery of particles, the unification of forces, the precise matching of theory and experiment. But here was a phenomenon that refused capture, that left only shadows and whispers. Still, the work continued. Each new map, each new survey, each faint supernova recorded on CCD sensors was another step into the unknown. The investigation had begun as a quest to measure the slowing of expansion. Instead, it revealed a universe whose deepest law seemed inverted, whose most ancient force carried within it the possibility of reversal. The deeper scientists probed the mystery, the stranger the story became. What had begun as a puzzle of faint starlight soon revealed itself as a challenge to the very foundation of physics. The universe was not only expanding faster, it seemed to be accelerating into a future both bewildering and ominous. Gravity's dual face on human scales. Gravity behaves as expected. It pulls the apple from the branch, keeps oceans tethered to the earth, and locks planets in their long ellipses. Around the sun, even across galaxies, its embrace is unquestioned, binding billions of stars in graceful spirals. But across the grandest expanses, billions of light years, gravity seems to wear a second mask. Instead of attraction, there is repulsion. Instead of binding, there is scattering. This duality unsettled the scientific mind. How could a single law yield to opposite outcomes? Was gravity itself more complex than Newton or Einstein imagined, or was something hidden interfering with its work? If space itself possessed energy, and if that energy exerted negative pressure, then the very fabric of reality could act as a force of repulsion. The equations suggested precisely this. Yet equations, though elegant, are indifferent to human comfort. They whispered of outcomes far beyond stability. The false vacuum, one of the most unnerving possibilities, emerged from quantum field theory, the concept of a false vacuum. In this view, the universe as we know it is not in its most stable state. Like a ball resting in a shallow dip on a hillside, the cosmos may only appear balanced. A deeper valley might exist, a truer vacuum of lower energy. Should a quantum fluctuation tip the universe into that state, the very fabric of spacetime could change in an instant. In such a transition, the rules of physics might be rewritten. Forces could alter, particles could vanish, even the constants of nature might shift. The cosmos would be remade, its previous order erased without warning. To inhabit a false vacuum is to live on borrowed time, and the accelerating expansion may be a symptom of that instability. Gravity itself, inverted at the largest scales, could be the telltale sign that the universe is precariously perched, waiting for collapse or transformation. The question of constancy, even if the vacuum is stable, another riddle remains. Is dark energy fixed, or does it evolve? If it is constant, like Einstein's cosmological term, then acceleration will continue forever, an endless scattering. But if it changes with time, then stranger fates loom. Some models suggest dark energy might grow stronger, its repulsion compounding with each epoch, driving the universe into runaway acceleration. Others propose it could weaken, perhaps even reverse, leading to cycles of expansion and contraction. Each possibility carries profound consequences. A constant energy points toward a slow fading of structure, a universe cooling into silence. A growing energy points toward violence, an apocalypse of tearing forces. The Big Rip, the most haunting scenario, has been given a name worthy of myth, the Big Rip. In this vision, the expansion of the universe does not merely scatter galaxies. It accelerates until every bond of nature is undone. First, galaxy clusters would unravel, the invisible glue of dark matter overcome by repulsion. Then galaxies themselves would dissolve, stars carried away from one another. In time, even the solar system would fracture, Earth losing its tether to the sun. The moon set adrift from Earth. The sky would become an ocean of fleeing lights. Every constellation stretched and broken, but the tearing would not stop at the cosmic scale. As acceleration intensified, stars themselves would rip apart, their atoms dragged across space. Planets would dissolve, mountains would separate grain by grain, oceans lifted into the void, and finally, the very atoms of matter would be torn asunder, their nuclei shredded, their quarks scattered. The universe would end not in fire or ice, but in disintegration, a silence so complete that even the building blocks of matter would no longer exist together. Whether the Big Rip awaits depends on the properties of dark energy, whether its pressure is merely negative, or more extreme, what physicists call phantom. If phantom energy rules, then the countdown to dissolution has already begun, measured not in trillions of years, but perhaps in tens of billions. In cosmic terms, the blink of an eye, the instability of understanding, these scenarios are not predictions, but possibilities. They reflect the limits of knowledge, the shadows cast by incomplete understanding. Yet even as speculation, they alter the way humanity sees its place in the cosmos. The universe is no longer a stable backdrop, no longer a stage of permanence. It is a dynamic, unstable entity, perhaps temporary, perhaps fragile. Gravity, once seen as the ultimate force of cohesion, now appears as something capable of betrayal. It binds the apple, the planet, the star, but across the infinite canvas it scatters. It carries within it both the promise of order and the seed of dissolution. A universe out of balance. What deepens the mystery further is the fine balance of forces. For billions of years, matter held sway, slowing expansion. Only recently, in cosmic time, did dark energy take dominance. The universe seems to have entered this accelerating phase precisely when beings capable of measuring it emerged. Is this coincidence, or is it a clue? Some suggest it points toward deeper principles, anthropic reasoning, multiverse hypotheses, the idea that countless universes exist with different balances, and only in one like ours could life arise. To question its fate, whether coincidence or consequence, the timing sharpens the unease. Humanity exists at a threshold moment in a cosmos that has only just revealed its repulsive half, the haunting possibility, and so the mystery deepens. Gravity is not what it seemed. The universe is not as stable as once believed. The equations point to futures both silent and catastrophic, to vacua that may collapse, to rips that may tear even atoms apart. Each observation, the dim supernova, the pattern of galaxies, the whisper of the cosmic microwave background, points toward a reality where the force that binds also carries the power to unbend. It is a haunting thought that in the heart of gravity lies its own inversion, that the great sculptor of galaxies may one day dismantle them, that the very fabric of the cosmos, in all its grandeur, is not guaranteed permanence. but may turn inside out, scattering the story of creation back into silence. The mystery of an accelerating cosmos left physics not with answers, but with questions vast enough to eclipse entire disciplines. If gravity, the most ancient of forces, can behave as if inverted, what mechanism lies at the heart of this reversal? Across laboratories, observatories, and chalkboards filled with equations, physicists turned from shock to speculation, and a spectrum of theories emerged, each bold, each incomplete, each straining to explain the unseen hand of dark energy. The cosmological constant reconsidered, the first and simplest explanation, was one already written into the history of physics. Einstein's cosmological constant, once abandoned as a mistake, returned as a candidate for the repulsive force. In this view, space itself is imbued with energy, not matter or radiation, but a property of the vacuum. Empty space is not truly empty. Even in perfect darkness, fields fluctuate, particles wink in and out of being, and the vacuum hums with invisible activity. The cosmological constant treats this vacuum energy as a fixed quantity, constant across time and space. It exerts negative pressure, pushing outward as the universe expands. The mathematics is elegant, the predictions stable. A cosmos that accelerates forever, driven by the unchanging tension of spacetime itself. But the elegance hides a flaw. When physicists calculate the expected energy of the quantum vacuum, the numbers miss reality not slightly, but catastrophically. The prediction overshoots observation by a factor of 10 to the power of 120, the most infamous mismatch in all of science. Why the vacuum should possess energy at all, and why it should possess exactly this minuscule amount, remains unanswered. Quintessence, a dynamic field. Others proposed that dark energy is not constant but evolving, a field that shifts across cosmic history. They named it quintessence, after the fifth element of ancient philosophy, an unseen substance pervading the heavens. Unlike the cosmological constant, quintessence is dynamic. It changes in strength, perhaps stronger in the past, weaker in the future. Its energy density evolves as the universe expands. In this model, acceleration is not fixed, but may accelerate further or even reverse. The fate of the cosmos becomes contingent, its trajectory sensitive to the properties of this mysterious field. Quintessence offers flexibility, a way to fit data without invoking improbable fine-tuning. Yet it carries costs. No known particle or interaction corresponds to such a field. It is a solution drawn more from imagination than evidence, a placeholder awaiting discovery, phantom. Energy and the Big Reaper, darker possibility lurks in the equations. Phantom energy. Unlike the cosmological constant or quintessence, phantom energy has an equation of state more extreme than -1. It does not merely resist compression, it intensifies with expansion, its density growing as the cosmos stretches. The result is catastrophic. Phantom energy drives the universe toward runaway acceleration, tearing galaxies apart, then stars, then planets, until even atoms are unraveled. This is the Big Rip scenario, a cosmic doomsday where not even the fundamental bonds of nature survive. Such a future would arrive in tens of billions of years, not tomorrow, yet uncomfortably near in cosmic terms. Phantom energy remains speculative, but its possibility haunts the equations. If observed, it would mean the universe carries within it the blueprint of its own disintegration. Modified gravity, perhaps the error lies not in the energy of space, but in our understanding of gravity itself. Einstein's relativity has passed every test in the solar system, in black holes, even in gravitational waves. Yet those tests span only certain scales. On the scale of the universe itself, perhaps relativity breaks down. Modified gravity. Theories propose that what appears as dark energy is instead a shift in the law of gravitation. Extra dimensions, hidden interactions, or corrections to Einstein's equations could mimic acceleration without invoking vacuum energy. Some models draw upon string theory, suggesting our universe floats as a brane within higher dimensions, with gravity leaking or inverting across invisible boundaries. These ideas offer daring alternatives, but they are perilous. Any change to gravity must match the exquisite precision of known experiments while explaining acceleration. To bend one part of the equation risks breaking another. Still, the possibility remains. Perhaps gravity itself is not as we think, and what seems like inside-out behavior is not inversion, but revelation. Echoes of inflation, the mystery of acceleration, also echoes the earliest moments of cosmic history. In the first fraction of a second after the Big Bang, the universe is believed to have undergone inflation, an exponential expansion driven by a high-energy field. Inflation smoothed the cosmos, seeded its structure, and then ended, leaving the hot Big Bang in its wake. Dark energy may be a distant cousin of that same process, a lingering echo of the repulsive force that once inflated the infant cosmos. If so, the universe may be caught in cycles of expansion, each driven by hidden fields that awaken and decay. The accelerating cosmos of today could be a faint shadow of the inflationary fire that birthed it. The multiverse and anthropic reason. Theorists take the mystery further, into realms almost philosophical. If the vacuum can possess many possible energies, then perhaps the universe we observe is only one among countless others, each with its own laws. In this multiverse view, we exist not because dark energy has a particular value, but because only with this value can galaxies, stars, and life emerge. It is not explanation, but selection. The cosmos allows observers only in rare pockets, where physics permits stability. This reasoning is controversial, for it edges toward the untestable, yet it reflects the desperation of a field confronted with numbers that resist explanation. If the vacuum energy is inexplicably small, perhaps the answer lies not in why, but in where, in the possibility that we are simply in one universe among many, a spectrum of uncertainty. Each theory carries its promise and each its flaws. The cosmological constant is simple but inexplicable. Quintessence is flexible but unverified. Phantom energy is mathematically possible but apocalyptic. Modified gravity is bold but constrained. Inflationary echoes are compelling yet distant. The multiverse is expansive yet intangible. No single explanation has triumphed. Observations narrow the field, but do not decide it. Dark energy remains a riddle, a whisper of physics not yet written, a clue to truths beyond today's frameworks. The philosophy of speculation is not failure. It is the frontier of science, the place where imagination and mathematics reach together into the dark. Theories of dark energy reflect humanity's attempt to confront the unimaginable. A universe where the force most trusted to bind might instead be unbinding. In this spectrum of possibilities lies a profound humility. Physics, so often triumphant in its predictions, finds itself on shifting ground. The cosmos is not merely stranger than imagined. It may be stranger than it can be imagined, and yet in this uncertainty lies possibility. To speculate on gravity, turned inside out, is to glimpse the edge of understanding, and to accept that the universe may carry secrets still waiting to be revealed. The mystery of gravity turned inside out could not remain only in theory. Science advances by measurement, by instruments reaching where the human eye cannot. If dark energy truly dominates the cosmos, if the vacuum itself carries the seed of repulsion, then its fingerprints must be traced in the faintest signals of light and matter. And so, humanity has turned its telescopes, satellites, and detectors toward the sky, building a global effort to confront the most elusive force. In nature, the watchers of the sky, the Hubble Space Telescope, launched in 1990, became the first great sentinel of this quest. Suspended above Earth's atmosphere, it observed distant galaxies and supernova with clarity impossible from the ground. It was Hubble's sharp vision that confirmed and refined the discovery of cosmic acceleration, turning suspicion into certainty. With its instruments, astronomers could push deeper into the past, measuring the faint glow of ancient explosions and charting the expansion history of the universe. Yet Hubble was only the beginning. The James Webb Space Telescope, launched in 2021, extended that vision into the infrared, able to pierce dust, to see the earliest galaxies, and to measure faint light stretched by billions of years of expansion. Webb's mission is not only to glimpse the dawn of galaxies, but to sharpen the timeline of acceleration, to ask whether dark energy has been constant or shifting. Each observation carries weight, each distant redshift another clue to the behavior of a universe in flight. Beyond these new instruments rise. The Veracruz-Rubin Observatory in Chile will soon begin its legacy survey of space and time, photographing the entire southern sky every few nights. Its data will reveal billions of galaxies, tracing cosmic structure with unprecedented depth. By mapping how galaxies cluster and how their shapes distort through weak gravitational lensing, Rubin will chart the tug-of-war between matter's pull and dark energy's push. Meanwhile, the European Space Agency has launched Euclid, designed explicitly to probe the dark universe. Its wide-field telescope will map the geometry of space, the distribution of galaxies, and the bending of light across billions of years. Together with Rubin, Euclid aims to measure whether dark energy is truly constant, or whether it evolves, a test that could distinguish between Einstein's cosmological constant and more exotic fields. The whisper of ancient light-while telescopes. Map galaxies. Satellites study the oldest light. The Planck mission, launched in 2009, carried detectors cooled to near absolute zero, sensitive enough to read fluctuations in the cosmic microwave background at the microkelvin level. From those ripples, scientists extracted the most precise values of cosmic parameters ever measured. Planck confirmed the picture. The universe is flat in its large-scale geometry, filled with 5% ordinary matter, 25% dark matter, and 70% dark energy. The echoes of the early cosmos, frozen in the microwave background, spoke with harmony. Acceleration is real, the balance of energy undeniable. Yet even here, puzzles remain. Different methods of measuring the expansion rate, the Hubble constant yield, conflicting results. Observations of the CMB suggest one value, while local measurements of supernova and galaxies suggest another. The tension is not minor. It hints that something fundamental may be missing, that dark energy is not so simple, or that gravity itself requires revision. This Hubble tension has become one of the central battlegrounds in modern cosmology, a crack that may widen into revelation, the language of particles. While astronomers gaze outward, physicists turn inward, probing the vacuum itself. In particle accelerators, like the Large Hadron Collider, protons collide at near light speed, recreating conditions of the early universe. Though the Higgs boson has been discovered, no particle has yet been found that explains dark energy. Still, the collisions test theories of vacuum stability, searching for signs of hidden fields or instabilities that might betray a false vacuum. The vacuum, after all, is not emptiness, but a seething sea of quantum fluctuations. Virtual particles erupt and vanish in femtoseconds, and fields ripple beneath the surface of reality. If dark energy is truly the energy of the vacuum, then it is this restless ocean that carries the secret of repulsion. But why the ocean whispers so softly when theory predicts it should roar remains the most stubborn question of all. The music of spacetime and other frontier lies in the detection of gravitational waves, ripples in spacetime itself. Since 2015, the LIGO and Virgo observatories have captured these waves from colliding black holes and neutron stars. Though not directly tied to dark energy, gravitational waves offer a new language for cosmology. By measuring how these waves stretch as they travel, astronomers can test the expansion rate independently of light. These standard sirens may soon provide a new measure of cosmic acceleration, a fresh vantage on the inversion of gravity. Future observatories, like the space-based LISA mission, will listen to lower frequencies, tracing the slow dance of supermassive black holes. In their patterns may lie clues to the structure of spacetime on scales untouched by light. Each wave, each vibration of the cosmic fabric is a probe into the unknown. The patience of science together, these instruments form a chorus. Telescopes, satellites, colliders, detectors, each a different sense, each attuned to a different signal. No single measurement will solve the riddle. Only the convergence of evidence, the harmony of many voices, can bring clarity. The search is not swift. Decades pass between conception, construction, and observation. Data trickle slowly. Analysis takes years. Yet the patience of science mirrors the patience of the cosmos itself. The universe has carried its secret for billions of years. It will not yield easily. The unfolding of possibility with each observation. The possibilities sharpen, is dark energy. Constant, a quiet hum in the vacuum, or dynamic, shifting with time. Is the acceleration gentle, or does it hide a catastrophic future? Are the laws of gravity themselves incomplete, requiring a revision as radical as Einstein's a century ago? The tools of science do not answer yet, but they illuminate the path. They reduce uncertainty, constrain speculation, and reveal the limits of the possible. In their slow accumulation, a new portrait of the cosmos begins to emerge, one in which gravity, the ancient binder, carries within it a paradoxical face. The work continues. Night after night, observatories track galaxies, satellites record photons, detectors wait for ripples in spacetime. Humanity watches, listens, and measures, knowing that the answer to the greatest mystery may arrive not as a sudden revelation, but as the quiet convergence of countless observations. And in that convergence lies the possibility of truth, the moment when gravity's hidden nature, its inside-out secret, is finally revealed. There is a moment, after the equations and the measurements, when silence falls. The telescopes rest, The satellites orbit in quiet arcs, and the detectors hum in the dark. Beyond the noise of data, beyond the clash of theories, lies the question that science alone cannot dissolve. What does it mean to exist in a universe where gravity itself may turn inside out? The fragile balance of reality, the cosmos, once appeared eternal, a steady firmament above human lives, unchanging in its vastness. But the discoveries of the past century have stripped away that illusion. The universe is not static, not safe, not permanent. It grows, it evolves, it accelerates toward futures that resist comprehension. Gravity, the force that binds, has revealed its second face, a hidden repulsion woven into the fabric of spacetime. On the scales of apples and planets, it pulls faithfully downward, but across the gulfs between galaxies, it pushes, scattering creation outward in a restless tide. This duality reminds us that stability is an illusion. The balance of expansion and attraction is not timeless, but temporary, a delicate equilibrium destined to shift. Matter once held sway, now dark energy rules, and the moment humanity arose to measure the heavens coincides with this cosmic transition. A coincidence, perhaps, or perhaps a reminder that the universe is not obliged to mirror our expectations. The impermanence of structure of dark energy is constant. Then the universe will stretch forever, galaxies drifting beyond reach, stars burning out, matter decaying into silence. If phantom energy lurks, then all bonds may one day unravel in a rip so complete that atoms themselves dissolve. If the vacuum is false, then in an instant the cosmos may be rewritten, laws reshaped, history erased. Each scenario shares a common truth: permanence is an illusion. Stars are not eternal. Galaxies are not eternal. Even gravity, the architect of structure, may not be eternal. The universe carries within it the seed of its own undoing. As if creation and dissolution are written into the same script, humanity's place in the vastness too. Dwell within such a universe is to live within. Paradox. On one hand, we are inconceivably small, fragile beings bound to a single planet orbiting a single star. On the other hand, we are the only creatures we know of who have measured the acceleration of the cosmos, who have glimpsed the inside-out nature of gravity itself. This knowledge is humbling. It reminds us that the universe does not exist for us, nor align itself with human hopes. Yet it also reveals that we are participants in its story, fragments of matter aware enough to trace the fate of all matter, patterns of consciousness, capable of reflecting on the impermanence of the very fabric that sustains us. The echo of Einstein's mistake in this light. Einstein's so-called greatest mistake becomes something else entirely. His cosmological constant, once discarded, may in fact be the truest description of reality we have. Perhaps he glimpsed, if only briefly, the inversion at the heart of gravity, the possibility that space-time carries within it both attraction and repulsion. If so, his equations whisper a profound truth. The universe is not bound by human expectation. It is stranger, subtler, and more paradoxical than even its greatest thinkers imagined. The philosophy of the unknown to accept this is to embrace uncertainty, not as failure, but as essence. The mystery of gravity turned inside out is not only a scientific puzzle, it is a philosophical mirror. It shows us that even the most familiar forces can conceal hidden faces, that reality itself may harbor contradictions beyond comprehension, and it invites reflection on what it means to live in such a cosmos. If nothing is permanent, not stars, not galaxies, not even the laws of gravity, then meaning cannot rest on permanence. It must rest instead on presence, on the fragile gift of awareness within a universe that will one day scatter our atoms into silence. The final reflection. Perhaps this is the ultimate message of dark energy, the ultimate lesson of gravity inverted. That creation and dissolution are not opposites, but partners. That the universe binds in order to unbind, gathers in order to scatter, begins in order to end. Humanity stands in the brief middle chapter between the fire of the Big Bang and the silence of what comes after. To witness this, to measure it, to ponder it, this is our role in the cosmic drama. The final thought is haunting, yet beautiful, that gravity, the silent sculptor of galaxies and stars, carries within its nature the possibility of inversion. That the universe, in all its immensity, is not eternal, but impermanent, and that, within this impermanence, lies the truest mystery of all, that we are here now aware of it. The cosmos may one day scatter into nothing, but for a fleeting moment, in the thin sliver of time we call the present, it gathers itself into beings who can wonder, and in that wonder, the universe, turning inside out, finds its reflection.